Now this problem 13 deals a little bit with this Watati-Benioff zone, and we're going to compare our answers for questions 9 through 12 and choose a statement that best describes your observation. So subducting slabs must reach a depth of, nope, that's incorrect. Subducting slabs must reach a depth of 101 to 200 kilometers before, yes, that's true. And our trench caps are essentially, no, they're not the same around the world because one was remember this one was 295 and the other one was only about 190, right? So they're quite a bit different there. And the subducting slab has a steeper angle of descent in the larger, no, that's incorrect. It would have a shallow angle. It would actually be opposite. So this is the one that's correct right there. So for question 14, we're going to look at the, again, Tonga Trench and Nazca Trench. And we're going to calculate the angle of descent. So this is a little bit of trigonometry, and I kind of worked it out a little bit. So let's just look at how we're going to do this. So for the Tonga Trench, we had a depth. So they want us to take the average. So we picked between 100 and 200 kilometers depth for where the partial melting occurs and the hydrous flux melting. So the average is 150. So we'll take 150 kilometers. And then we're going to divide it by the R trench gap. And for the Tonga Trench, it was 190 kilometers, right? And we get an answer there. And then we want to take this tangent, which is arc tangent. And the way to get to it, I just clicked this second here and got to it. But you want the arc tangent. So if you select that, you get about 38 degrees. And so there's a couple of options. So it's either this one or this one. But now for the Nazca Trench, we had the depth of 150 and a distance of 290 kilometers. And then if we take the inverse tangent, we get about 27 degrees. So here's our answer right here. So Tonga is about 38. The Nazca is about 27. So all I did, I took the depth, which was 150 for both of them, 150 kilometers, divided by the distance, the arc trench gap, and then took that arc tangent. Now for question 15, we're looking at, again, we're going to select the seafloor edges again, and then we're going to make transparency of it, and then and so we already have this turned on. In fact, we'll make sure we have the earthquakes and the tectonic plates turned on, and we'll see what happens. So this is for question 15. So we did those two already. And then let's turn on the seafloor again. And then we'll already have it sort of semi-transparent there. All right, so let's go to question 15 west. So here we're flying to the MidAtlantic Ridge, and we're seeing this place marked 15 west, which is on this plate here. The 15 in the middle, right, which is right at the transform fault, and then problem 15 east. So these place marks point to a segment either on an active transform fault or an inactive fracture zone, right? So remember, the only active part is this blue line. That's a transform fault. These are just fracture zones, which are inactive. So problem 15 west and problem 15 east are inactive fracture zones. And actually, this is the correct one. All these other ones are incorrect. So problem 15 west, that's inactive. It's on a fracture zone. It's not on a plate boundary. Only the middle one here is on the plate boundary. Again, this is problem 15 east is not on the plate boundary. So you would select this first one here. For question 16, what direction are the place marks for problem 16 north and south moving respectively? So let's look at both of those, 16 north and south. So here's north. So north is moving off toward the east. South is moving off toward the west. So north is moving east. South is moving west. So it's that first one there. And then for problem 17, we're looking at what's going on with these place marks here. So let's select both of those. So they're both on this plate that's off here to the west. So they're both moving westward, right? So everything from the Mid-Oceanic Ridge is moving westward here, moving west. So both moving west. Both moving west. For problem 17. Problem 18, we're looking at the San Andreas Fault. Actually, this is a pretty good one here. This is down in Southern California. We'll select that one, and let's just fly to Southern California, we'll see the San Andreas Fault here. Yeah, so there's the San Andreas Fault. So the drainage is coming down off the San Gabriel, San Bernardino Mountains here, and then moves off toward the right here. So this would be an example of a right stepping or right lateral fault. So that's this option right there. Question 19, we're looking at hotspots. We want to figure out how fast the Pacific Plate is moving over the Hawaiian hotspot, and we're going to measure a distance between the Midway Atoll and the Kilauea volcano, and they want us to do it in centimeters, right? So let's see. So we got the seafloor ages map, and then I think all this is turned on. Let's make sure we have the. Well, let's turn on the volcanoes here for Hawaii, and then we have the seafloor ages turned on. We do, and then we have the earthquakes selected as well. All right. So let's fly over to this problem 19, which deals with Hawaii. So we'll select these two. So in this one here, they're going to have us measure the distance between the active volcano in Kilauea, which has volcanoes and earthquakes on it, and this Midway Atoll. And again, we want to do it in centimeters. So we'll take our ruler tool, select centimeters, and then we'll click over here on Midway, and then we'll go all the way over here to Kilauea, and it gives us about 245.2 million centimeters. And then note that the age at the Midway Atoll is 27.7 million years old. So remember this number, 245.2 million. So what we do here, we take the 245.2, which is 200,000, right? And we're going to divide it by the 27,700,000. And we get 8.9 centimeters per year. So, and there it is, 8.9 centimeters. So we'll pick that one there. So that's how fast this Pacific Plate is moving over this hotspot, right? So 27 million years ago, Midway Atoll was the active volcano. Now, if we look at question 20, we're trying to figure out the age of the bend in the Emperor Seamount Change. And so that bend is right here. And it's the age of the volcano, so we're picking about 41, 43 million years. That's the best option there. For question 21, we're looking at the Yellowstone hotspot. We're going to do something similar. We're going to use the Path tab to figure out how fast the North American Plate is moving over the Yellowstone hotspot. So let's select the Yellowstone hotspot, and we'll go to problem 21 and see how quickly the North American Plate is moving. So here's the Yellowstone hotspot. You can see the North American Plate is moving off toward the southwest because these volcanoes were once here and have since moved to their current position. So again, we'll select the path, and they want us to do it in centimeters, so we'll keep the centimeters. And so we'll start here, and then we'll just start moving really the centers of each of these. And we'll end up at the Yellowstone hotspot. So that gives us about 66.3 million centimeters. I'll just round it to 66.3. And then the age is, they want us to use an age of 16.5 million years. So in this case, we take those 300,000, and we're going to divide that by 16,500,000. And we get 4. We get 4 centimeters per year. Well, there it is, 4.2. Now, the last question is, well, what's the relationship between Hawaiian Seamount, the hotspot, and the Yellowstone one is? So the Pacific Plate is moving northwest at about, no, it's moving about twice as fast. But the Pacific Plate is moving northwest, about twice the rate of the southwest. Yeah, so this is the correct answer there. So anyways, I hope that helps out there. Well, let's see what we did here. We'll submit the quiz. And, oh, we missed one. Which one did I miss? So this one, I picked the west side. No, it's actually the east side that's moving more quickly. The east side is moving. I had those mixed up, but this is correct. The east side. But other than that, we did a pretty well job here. All right, well, let's stop here.